Conservation of energy. Energy is conserved when the initial energy equals to the final energy. You have potential energy represented by U, which is mgh, gravitational potential energy. Kinetic energy, which is represented by 1/2 mass times velocity squared. And we could have final kinetic and final potential. When we have rotational motion, we can also have kinetic energy from rotation. This is equal to 1/2 I, which is the moment of inertia, times omega squared, which is angular velocity squared. As noted in the previous videos, I is the moment of inertia, and it changes depending on the distribution of mass. For the AP test, you need to memorize mr squared. Everything else will be provided for you. Just like linear motion, each object can have a potential energy if there is a height. It could also have a kinetic energy, 1/2 mv squared. This is known as translational. Remember, translational motion means it could go in the X, Y, or Z direction. And it could have rotational motion if it's spinning. Non-conservative forces, the total energy is not conserved. So if you write initial energy is equal to the final energy, you must place work due to friction or thermal energy at the end to make the equation equal to each other. Or the other way you could write it is the work due to friction or thermal energy is equal to the energy final minus the total energy initial. And if it's not conserved, this will not equal to 0. We have solved this problem in class multiple times when we did the work and energy unit. We have an object sliding down a hill, height h, from rest. Find the velocity at the bottom of the hill. Since we assume that it's frictionless initially, we know that the energy is going to be conserved. So the mechanical energy initial must equal to mechanical energy final. Possible energy is potential plus kinetic. Possible energy at the end is potential and kinetic. At the beginning, since it's starting at rest, there is no kinetic energy because there's no velocity. Since we have height, we're going to have potential energy, which is mgh. At the end, there is going to be no potential energy because it is at the lowest point. And kinetic energy is what it's going to have. So this becomes 1/2 mv squared. The masses cancel out because it's the same. And if I rearrange, this becomes 2gh square root. Let's say now, instead of having a box sliding down the hill, we have a sphere rolling down the hill. Since it's rolling down the hill without slipping, energy is also going to be conserved. We're going to also start with mechanical energy initial equal to mechanical energy final. At the top, we could have potential energy. We could have kinetic energy translational, that is moving in the X, Y, Z direction. And we could have kinetic energy rotational because now it's rolling, so it's spinning. At the end, we could have potential energy final, kinetic energy translational. I put the prime to represent it is a different kinetic energy from before, and rotational energy prime. Since the object is starting at rest, we know it's going to have no translational energy because my velocity, remember, 1/2 mv squared is going to equal to 0. It's going to have no rotational energy either, kinetic energy, because it's at rest. And if I plug this in, this is 1/2 I omega square. Since it's not slipping, omega was V R omega. So if I plug that in, this is 1/2 I V over R square. And since it's starting at rest, this V right here becomes 0, so it cancels out. So there's no rotational energy. It will have potential energy because it has height of h. It has no potential energy final because there is no height at the bottom. It will have translational kinetic energy because it's moving, so that's 1/2 mass velocity square. And it will have rotational because it is rolling, so therefore it is spinning. So this is going to be 1/2 I omega square. So this is my generic formula. I could substitute in. So this is mgh 1/2 m velocity squared plus 1/2 I for a sphere is 2/5 mr squared. So that's 2/5 mr squared. And we said omega, remember, tangential velocity is v equals to r omega. And this is only true because it's not slipping. So this is equal to v over r squared. Now I'm going to simplify. Since the object is of the same mass before and after, all the masses cancel out. I have an r squared, v over r squared, so the r squares will cancel out. If I simplify this, this becomes gh 1/2 v squared plus, there's a 2 here on the numerator or a 2 on the denominator, so this becomes 1/5 v squared, because this is omega squared, so it's v squared over r squared. I could simplify this by having common denominator, which is 10. So this becomes 710 v squared. If I rearrange this and solve for v, v is equal to 10 gh over 7 square root. So if you notice, when things are rotating, we must include rotational kinetic energy. So when an object is rolling without slipping, the potential energy will be divided between the translational kinetic energy and the rotational kinetic energy. This problem we did in class before, deriving the tangential acceleration. So I'm going to quickly derive it using the torque formula. To do that, remember, we always start by drawing a free body diagram for each object. So the mass of the object, m1, is going to have the weight 1, and it's going to have a tension. The torque itself is going to be produced on the pulley because it's going to have a tension on the right side due to the mass. The T's are the same. It's also going to, if I draw my free body diagram, it's going to have a normal at the pivot, and it's going to have a weight of the pulley. So if I write my equation for my mass 1, the direction we're moving down, is going to be positive. So my sum of Fy is going to be Fg1 minus T equals M1A. And so we need to solve for T. So this is FG1 minus M1A. My torque equation is Fr equal to moment of inertia I times the angular acceleration. I'm going to substitute in for my force, which is the tension here. So that's Fg1 minus M1A times R, which is the radius, equals to I. Remember, I of a pulley is 1/2 mr squared. And alpha was a tangential radius times alpha. So if I plug this in, this becomes 1/2 mass of the pulley r squared. I'm going to substitute in for alpha, which is the tangential acceleration times r. And I'm going to do some simplifying here before I solve for A, the tangential. The r here cancels out with the r here. There's a r on top and an r on bottom, so they cancel out. So Fg1 becomes M1G minus M1A. This is equal to 1/2 the mass of the pulley times the tangential acceleration. We know since this moves as a system, my tangential acceleration has to be the same. So this is also a t right here. So solving for AT, I'm going to move the M1AT to the right side. So the top becomes M1G, and I could factor out an A on the acceleration, so M1 plus MP over 2. This is my tangential acceleration for the system. After finding the tangential acceleration, you could find the velocity, the time, and the height that the box travels to the ground by using any of the linear kinematics equation. Or you could use the second method to solve, using the conservation of energy. We know that the energy before must equal to energy final. Each object can have a potential energy if there is a height. Each object can have a translational kinetic energy if it's moving in the x, y, or z direction. And it can have a kinetic rotational energy if it's spinning. So potential energy of the pulley plus the potential energy of object 1, kinetic energy translation of the pulley plus the kinetic energy translation of the box, or 1, plus the kinetic energy rotation of the pulley plus the kinetic energy rotation of the box 1. These are all the possible initial energies. This is equal to the final energy. The final energy could be the potential energy of the pulley prime, because it's different from the initial. Potential energy of the box prime. The kinetic energy translation of the pulley prime plus the kinetic energy translation of the box prime plus the kinetic energy rotation of the pulley prime plus the kinetic energy rotation of the box prime. So these are all the possible energies. Since you have two objects, each of them can have a potential energy, a translational kinetic energy, and a rotational kinetic energy. So the pulley will have no height. The reason it will have no height is because its height at the beginning and at the end is going to be the same because the pulley does not move in the vertical direction. So that could be canceled out. The object of mass 1 will have height because it has the ability to fall. So M1GH. The pulley will not have a translational kinetic energy because it is not moving in the X, Y, or Z direction. It is only rotating. The mass 1 will have no kinetic energy translation initially because it is starting at rest. The pulley will not have rotational energy initial because it is not spinning until the block starts to fall. The block M1 will have no rotational energy because it's only moving in the linear direction and it is starting at rest. At the end, block 1 will have no potential energy because it has fallen through the entire height. The pulley will have no translational kinetic energy because it is not moving in the X, Y, Z direction. The block M1 will have translational energy, its maximum height. The pulley will have rotational energy because it is spinning. The block will have no rotational energy because it is not spinning. So the generic equation is the potential energy of the block will equal to the kinetic energy of the block, which is 1/2 1 V squared, plus 1/2 the rotational energy of the pulley, which is I omega squared, and I of the pulley is equal to 1/2 mr squared. The rope is not slipping. We could use V is equal to R omega. This is only true if it's spinning without slipping. So if I plug the numbers in, this is M1H 1/2 M1 V squared plus 1/2 mr squared V over R squared. So at this point, I could simplify some of the math. It's R squared down here. This is a R square, so they cancel out. So this becomes 1/2 M1 V squared plus 1/4 M of the pulley V squared. This is equal to M1GH. Since the objects are connected together by a rope, their velocity is going to be the same. So I'm going to solve for V by factoring out a velocity. So M1GH is equal to 1/2 M1 plus 1/4 MP. This is equal to V squared. So if I solve for V, V is going to equal to M1 GH over 1/2 M1 plus 1/4 MP square root. So if I make it a little bit cleaner, this is just M1 over 2 plus M the pulley over 4 square root. So whether you use the first method using the torque and then kinematics equations, the linear kinematics, to solve for the final velocity, time, or the height, or you could use the conservation of energy, you'll still get the same answer. The only thing is, if you are using the conservation of energy, make sure there's a potential kinetic, translational, kinetic, rotational for each object. You do not have to write every single equation out, but you need to note that all three energies are possible for each of the objects. This is an Atwell machine, and we derive the tangential acceleration using the torque equation. I'm going to quickly derive it again, and so we could compare it with the conservation of energy equation. So for each object, we must draw a free body diagram. So for M2, we're going to have a Fg, the weight of 2, and tension 2. On M1, we're going to have the weight 1 and tension 1. If the pulley was massless, since this is one rope, tension 1 and tension 2 will be equal. Since the pulley is not massless, there is a torque produced by tension 1 and tension 2, and the torques will be dependent on the weight and the acceleration. So the pulley will have a tension 1 on the right side, a tension 2 on the left side. In the middle, it will have the weight of the pulley, and then you will have a normal of the pulley from the pin. Since mass 1 is greater than mass 2, this pulley is going to rotate in the clockwise direction. General formula for torque is force perpendicular to R equals to I, moment of inertia, times angular acceleration. The force is going to be produced by the tensions of the rope. The normal and the weight of the pulley will have no effect because it is resulting from the pin, so the R is equal to 0. So if I look at my force, since it's going clockwise, I'm going to make the direction I'm moving in positive. So this is going to be T1 minus T2 times R. And I could subtract T1 and T2 first before multiplying by R, because the R's, or the lever arm, or the radius from the pivot point is the same for both. This is equal to I, and remember I for the pulley is 1/2 mr squared. Tangential acceleration is R, angular, so this becomes 1/2 mr squared times tangential acceleration divided by R. So to find the tension 1 and 2, we need to write a sum of Fy for sum of Fy is equal to T2 minus Fg2 equals to M2A. T2 is going up because M1 is going down. So if I solve for T2, this becomes M2A plus M2G. For the second equation, since it's moving down, Fg1 is positive minus T1. This equals M1A. Solving for T1 is M1G minus M1A. So substituting in for T1 and T2, so this is M1G minus M1A minus T2, so it becomes minus M2A minus M2G times R equals to 1/2 mr squared tangential acceleration over R. And simplify some math. There's a R squared, there's a R on the numerator, R on the denominator. Since this is moving as 1, all the A tangential are going to be the same, so this AT is the same as this AT and this AT. Move all the quantities with AT on one side and solve for AT by factoring it out. So AT becomes M1 minus M2 times G, because both of them are multiplied by G, divided by M1 plus M2 plus mass of the pulley divided by 2. So this is the tangential acceleration for the system. It is the same for M1, M2, and the pulley because they're tied by the same rope. If you want to solve for velocity, time, or height, you can use linear kinematics equation and solve after solving for the tangential acceleration. The second method we're going to use is the conservation of energy. We know that energy is conserved because there is no friction, there is no slipping, and it is rotating. So that tells us that the energy before and the energy after has to be the same. The possible energies before are the potential energy, kinetic energy translational, and kinetic energy rotational. Same goes at the end. We could have potential energy, kinetic energy, plus rotational energy. Again, for each object, you could have each of these energy. So M1 can have potential, kinetic translational, kinetic rotational. So goes for the pulley, so goes for M2. We know that M1 is going to fall because the mass of M1 is greater than M2. If M falls, the height that is going to fall, H, is going to be same as the height that the M2 is going to gain on the opposite side. To make my calculations a little bit easier, I'm going to assume that there is no potential energy at the beginning for both. M1, M2, and the pulley do not have a translational motion because everything is starting at rest. There is no rotational motion because they're starting at rest. So my initial energy is going to equal to 0. So by convention, falling is negative, so the potential energy of M1 is negative. So negative M1 GH. The potential energy of M2 is going to be positive because it's moving up. And the H are going to be the same because they are tied by one rope. If M1 falls by H, M2 has to go up by H. Both M1 and M2 are going to have translational kinetic energy. It's going to be, their velocity is going to be maximum right before it stops. So we're going to have 1/2 M1 V1 squared plus 1/2 M2 V2 squared. The pulley will have no translational kinetic energy because it is not moving in the X, Y, or Z direction. M1 and M2 will have no rotational kinetic energy because they are not spinning. Only the pulley will have rotational kinetic energy, which is 1/2 I omega squared. And again, we said the pulley moment of inertia was 1/2 mr squared. And since this is not slipping, we know that velocity tangential is equal to r omega. Now I'm going to rearrange the equation by moving the potential energies to the left side and factoring out GH. When I do this, this becomes M1 minus M2 GH. On the right side, I could factor out 1/2 M1 plus M2 velocity squares. And we could do this because they're tied by one rope, so all the velocities are going to be the same. Plus 1/2, I is 1/2 mr squared. Omega is v over r squared. Factoring out, the r squared cancels out with the r down here. So this equation becomes 1/4 mv squared. So if I rewrite this, this becomes M1 minus M2 GH 1/2 M1 plus M2 plus M of the pulley, let me put a P here, divided by 2 V squared. I'm going to solve for V squared by dividing both sides. So M1 minus M2 GH. There's a half, so to get rid of it, I need to multiply by 2. So there's 2 up here. And this is divided by M1 plus M2 plus MP over 2. This is V squared. So let's say I need to find the tangential acceleration. We're going to use the kinematics equation, the linear kinematics equation. We know that V final squared is equal to V initial squared plus 2AY. Initial is 0. This is why the kinetic energy at the initial was 0. So this tells you V final squared is equal to 2AY. And what we solved here is also V final, because this is the velocity final that we solved for. So substituting that in, this is 2A. My y is the height. This is equal to 2 M1 minus M2 GH divided by M1 plus M2 plus MP over 2. Now I could cancel some values out. There's a 2 on top, a 2 on top, that cancels out. There's a h here and a h here. Final equation A becomes M1 minus M2 times gravity divided by M1 plus M2 plus MP over 2. If I check my equation, this equation down here by the conservation of energy looks exactly like the tangential acceleration I solved for using the torque. Both methods are correct. The first one, you would have to write your torque equation, solve for tangential, and use kinematics if you need to find velocity. You could use the conservation of energy if you want. Either method works.